Welcome, Julien. So hi, I'm Julien. So today I'm going to talk from flat file to deconstructed database. I'm kind of looking back at the past 10 years, and that should be interesting. So I'm a principal engineer at WeWork, so kind of working on the data platform and helping on like how do we build and scale the data platform at WeWork. So yeah, I co-created Parquet with the Impala team from Cloudera. I've been involved in a bunch of projects, so I got my first committership on Pig. I don't know if a lot of people use Pig today. And I was working at Arrow at the time, so I was lucky to use Hadoop early on in 2007. And after that, I worked at Twitter and Julien. Oh, this guy here, that's King Julien from Madagascar. We share the same first name, but I'm not going to do the dance. So the agenda today. So I start with, at the beginning there was Hadoop. It was 2005. But so then that's Mike Stormbreaker. And I say like, wait, like, what about all the database research we've been doing for 3 decades? And then I talk a little bit of what I mean by the deconstructed database and kind of look a little bit at the future where I see this is going. So at the beginning, at least for our time frame, there was Hadoop. So for the story, this is a picture of the original Hadoop toy that Dark Cutting named the project after. That's the real thing. So what is Hadoop? So when we talk about Hadoop today, there are a lot of stuff, but Hadoop originally is 2 things, right? A distributed file system and a processing framework, MapReduce. And they're both based on Google papers, and they're kind of 2 different abstractions, but they work well by being well integrated into each other. And so it's a great tool for looking for a needle in a haystack with no clause. And I have to admit, I stole this image from Dimitri, former colleague at Twitter. And it's kind of, what I mean is like, you kind of scale a lot of things. You have a big task, you can use Hadoop and it's going to make it, but it's going to throw a lot of horsepower. It is. It's kind of a blunt tool originally. And it's just like, you just throw a lot of machines at the problem and it's going to work. So how does it work? You have those 2 abstractions, right? One is the execution, the other one is the storage. So the execution has 2 phases, right? So you do a map phase and you read locally, and it's kind of designed to scan a lot of data sequentially on the local file system, and then it does a shuffle, and the abstraction is we're going to put all the values for the same key together so that, with that you can do aggregations, you can do joins, there's a lot of operation. You can do PageRank implementation by doing this. And then the reducer is going to take all those values, do something with it, and write the result locally. And so it's kind of simple. There's a lot of different algorithms you can use with that as a building block. It's composable, you can compose a lot of them. And the storage layer is a distributed file system, so you just store files in on multiple machines, and so it gives you this abstraction. It looks like a single file system, even if it's distributed. But at the same time, the execution layer knows exactly where the data is stored, and so it can schedule the task to scan every subset of the dataset locally. And so back in the day, moving the execution local to the data was a big deal because there was a big difference in I/O between the local file system and the network. And so that was the general idea. So as long as the shuffle is not sending too much data and you kind of minimize how much data you send over the network, it's fairly efficient. So now let's talk about that guy. So who knows who that is? Woo, that's it. Come on, guys. So this is Michael Stormbreaker. This is a Turing Award winner, Michael Stormbreaker. So look it up. Everybody who didn't raise their hand. He's famous for his work in databases, in particular Postgres, and more recently Vertica. And so he's what we colloquially call in the industry not a bozo. So usually I get loves with this. Not a bozo. That's Michael Stormbreaker. So and so it's famous. So like in like Hadoop started in like taking off in 2007. So it's famous to have written this blog post. Was like, this is a major step backwards. You guys don't know what you're doing. Why are you doing this file system scan thing when we've been working on databases for 30 years and we told you about indices, how to link the data differently, how to make things more efficient. And so, you know, what's going on? You're just like reinventing the wheel and in the bad way. And so it's kind of, you know, he was making a point. After all, this is Turing Award winner Michael Stonebrook. And so let's look at what we have. So we have the relational model, you know, first described in 69. SQL came soon after that in the early 70s, and then it was standardized in 86, and then, you know, listed all the years there have been revisions. So it's been around for a long time. And so all over that time, it became a global standard. It's a universal data access language. It's widely understood. And there are a lot of good reasons for it. Right, so the underlying principles, there's kind of separation of logic and optimization. I don't know if you ever wrote a MapReduce job, but basically if you want to make it efficient, you take your logic and start like writing it against MapReduce to make it really efficient. So you do things in a certain way. So you very quickly, you can't touch the code anymore, right? Because it just becomes very complex. You tie together logic and whatever you have to do to make it fast. And it's really painful. So SQL, you just express what the logic of your application is, right? So you define all the tables you need. You define all the constraints, you don't even need to explain how you want the join happening in what order, right? So this is all the job of the optimizer. And so the optimizer is factoring out all the complex logic and how do we make things fast, right? So you just take, this is the result I want, and the optimizer is going to figure out how to actually achieve that. So that's the first very good aspect of this. And it's all powered because we have the SQL language, which is a higher level language that then gets translated into lower level operations. It's standard, so like once you start to use SQL, you can use a lot of tools together. And you also have other aspects that, you know, it depends if you're doing transactions or if you're doing like more OLAP analytical queries. But you have this notion of having foreign keys, having transactions, making sure your data there's integrity and it's not just like random things pointing to flat files. And the other aspect of this is schema evolution. You can build views. When you update your schemas, you have ways to understand that it's going to be compatible or not. And so if you compare abstraction from MapReduce and the file system to a database, in database, the storage is hidden behind the notion of tables. So tables have a name and a schema. And you don't need to, when you query them, you don't need to know what file format is used. You don't need to know if there are indices. You don't need to know there are statistics, if it's partitioned, if it's stored. It's all that's happening under the hood that the optimizer looks at and decides, you know, if it can do faster because of all those characteristics. And on the execution level, you have SQL. So instead of having opaque function like in MapReduce runs opaque function. Let's map this function on top of things. Or let's map this function on the reduce side on top of the groups of values. Instead, you have a well-described language with a lot of operation that the optimizer fully understands. And it understands what field you're accessing, what you're doing with them, how you do your join. And so, you know, there's a lot of room for optimization. So if we look at the steps of a query evaluation, we start from parsing the SQL, so understanding the syntax. And then we look at what the schema, what field, so we know what field is coming from our table. And possibly you have statistics attached to this. And you feed that into the optimizer that's going to translate the logical plan, which is what you join with what features you apply, and take that and feed that into the optimizer to produce a physical plan, which is actually what are we going to do. Things like pushing down features, projection into the scan layer, and like trying to build the most efficient plan for your data, depending on the layout, the size of the tables, the hierarchy of the relations, and how many different keys you have in that. And finally, it gets fed, into the execution layer that's going to take that physical plan and produce the actual results of the query. And so if you look, this could be like, you know, an architecture diagram of something like Vertica, for example. And so if you look at how that works, you know, you take your query, you parse it, you get AST, a syntactic tree of your query. Then you go in the semantic layer, you get more information about what their schema, what column comes from what table. Feed it through the optimizer, get a physical plan, and then you get to the execution layer. And in that example, I'm taking the advantage, I'm talking about Vertica because that could be a distributed analytical database with columnar representation. So columnar representation enables things like fast projection pushdown, faster vectorized execution, and all those kind of things. And usually you push down as much as possible in the CAT-scan layer, and eventually you present the result to the user. So it's kind of, it works well because the optimizer understands very well the characteristic of the execution, right? He knows how to pick the best join for the case and those kind of things. So it's like very well integrated, right? The optimizer needs to know is very tightly integrated with the execution layer, needs to understand very well what's going on to produce an efficient plan. So the next question is like, what was going through our minds when we all started to jump on the Hadoop train, and like when we all had nice databases, and really like, why did we get back to these very low layer blunt abstractions? So like, there are some, I'm going to try to explain the thought process and how I think this happened. So constraints are good, right? You remember how we separate. Constraints is what allows you to separate the logic from the actual representations. You know, like a schema, the schema abstraction in a database, it allows you to define your query and to have the optimizer like figure out, like the table abstraction abstracts out what file format I used, abstracts out if you have statistics, if you have indices, and that abstraction is what allows the optimizer to pick an efficient plan and decoupling all the concerns about how you execute it from the definition of the logic of what you're trying to achieve. So constraints are good, but we need the right constraints. So with SQL, you have actually, there are a lot of components and there are lots of layers, but we all get only the top level abstraction. And so in traditional SQL implementation, there's a lot of limitations, right? So in Hadoop, sorry, I'm jumping the gun on my next slide, so I'm not going to do that. So typically you have flat schema, you have kind of inflexible schema evolution is like when you change the type or when you modify a column, when you do something, it tends to kind of rewrite all the data to the new format, right? If you change from integers to string, you can do this, but it will rewrite the whole history. You don't have any lower level abstraction, so everything has to be through SQL. So it doesn't work well from other type of access to data if you're trying to think in terms of graph database, for example, use different layouts and different query languages because SQL is not well adapted to this. So you don't have lower level abstraction to use the lower component of the database, and it doesn't scale that well because it's trying to do it all, right? It has transactions and it has constraints, and you have like constraints on how you can do it and how you can evolve your schema. So there's a lot of constraints that make it a really nice, well-packaged solution. However, you cannot pick and choose some bits and like say, oh, I don't care about transaction. I don't care about like the SQL abstraction. I just want to go really quickly at the columns in a column database, right? You kind of all have to do in your column. When in Hadoop, instead of that, you know, you can do whatever you want. It's just you're just running code on files. So your files, there's no constraints. You experiment with different formats. You can experiment with different representation of data. You can have unstructured tests. You can have graph representation. You can have non-uniform schema. You don't have a constraint of rewriting all the data. So there's a lot of freedom to experiment. And it's just code, right? So you can do machine learning. You can do a lot of things. And I think the key part is it's open source, right? So you can, and unlike Vertica, for example, you can pick and choose different pieces. You can fork it. You can say, I don't care about that part. And you can start modifying things. You can build on each other, right? We can all contribute to what's going on. And so that's has been a key part of how Hadoop has evolved and how it's been powerful. And when you pick a database, you kind of have to pick the whole package, the whole nicely, well, vertically integrated solution. But that's it, right? You can't, it's like when you look at your car today, you know, people used to fix their own cars. Now if you open the hood, it's just like nice and shiny, but you can't really do anything yourself on it. And so, you know, Hadoop is so flexible and composable, then you can actually implement SQL with it. Which gets to my, and you can actually implement SQL with it. And of course they did, right? So Hive was open source in 2009. So if you follow the dates, like Hadoop started picking up 2007, 2008. Stonebreaker was saying, hey, like we have SQL, what are you guys doing? 2009, they've been working on for some time, but like, hey, look, we did SQL here. And of course, Hive doesn't work like this anymore. But basically, if you look at all the steps, the original Hive was like, oh, we take a query, we parse it, and you know this logical plan, we just like turn it into MapReduce. So it's just composing those snowplows operators that you showed a lot of. So of course, there was a lot of latency, like storing a lot of horsepower to the problem. So of course, Hive doesn't work like this anymore, but it started like that. So now, fast forward 10 years later, and that's where we get to what I was calling the deconstructed database. So I don't know if you follow kind of the food trends and stuff. So this is a deconstructed bento box. So you know Mackey's and stuff that you know you raw and everything. So it's kind of deconstructed is you get all the ingredients separately instead of you take a very elaborate dish and you just like put all the ingredients separate on the plate, and this is a deconstructed thing. So if you're more of technical types, you know, engineers and stuff, this is a deconstructed typewriter. And you know, I'm going to overlay my, if you're tired of my analogies, I'm going to overlay the components, you know, so it's kind of, there are a bunch of components, and I'm going to switch to the open source world and the Hadoop ecosystem. You know, they have like query model, data exchange, string processing, batch execution, storage. So you have all those components that work together. And the reason I'm calling this deconstructed is because you have all those components and you can pick and choose and use it in different ways. So I'm sure you've seen a lot of those slides. You know, put all the icons together. This is my slide. I made this one. Everybody, you know, like everybody has a picture of a sunset. I have a slide of the Hadoop ecosystem. And so, you know, everybody's using the Hadoop ecosystem. And today, you know, people use the Hadoop ecosystem. They don't even use Hadoop anymore. They store their data in S3. They use Spark to execute. But they use all the components that started around this Hadoop thing. And, you know, and that's kind of, I narrowed down only to open source things. But it's kind of, I'm just trying to say, hey, look, you have this storage component, you have these string processing components, you have these execution components, and it's kind of a lot of SQL and Hadoop thingies. You know, started with Hive, but not a lot of them. I've seen the creator of Phoenix, Apache Phoenix in the room. Hey, James. And you have all those things, but the key part is they're all open source, and they're all kind of building on top of each other. And it's really interesting how you can start looking at this, and there's some like core components that are coming out of it. So, you know, things you want to look at when you look at all these components and how they fit together, and how do you deconstruct these databases in different elements. right? So there's a storage piece. It can be raw-oriented or columnar, immutable or mutable. There's string storage, and there's kind of analytics optimized abstract storage. There's a whole query model when you have things like SQL, you have more functional-oriented things like big, like cascading, or the creator of cascading is also known. Things like that. And then you have the machine learning aspects, where you have different things. There's things that have been built on top of Spark. You have TensorFlow, you have different frameworks existing. Data exchange, against you have things oriented like Avro, which is pretty much a standard now. Columnar-oriented like Arrow, and streaming execution. You have things started with Storm, and today you have a bunch of different options. And in batch execution as well, you know, like you had MapReduce originally, and you had things like cascading, things like Spark that have existed, and that kind of improving that model. And so there are a bunch of components. There's kind of areas that are emerging, and there's some standard components that are doing key part of the database that are emerging. So, you know, so I'm the Parquet guy, so I'm a little biased. But on the columnar storage side, you have Parquet that kind of became the de facto standard of at-rest storage. On the SQL parsing and optimization, you remember this optimizer, key component of the database. Calcite is one of the least known and more powerful components of this whole ecosystem. We use in many projects to optimize a query. In the schema model, I think we can agree that Avro has become the standard. Some people use Protobuf, some people use Thrift. I used to use Thrift. I would recommend Avro. You know, columnar exchange. Arrow is becoming the standard of how you exchange data in an efficient way. Right? You see work going on. And on the table abstraction layer, you know, we used to use the Hive Metastore, and I think it's one we used it because that's what there was at the beginning. It's kind of grew organically. But now that I've been working 10 years on that ecosystem, things like Iceberg, and on our end, we're working on Marquez as more of a metadata layer, are going to become more and more important. And so if we look at Calcite, so it's kind of, I'm going to reuse that picture I did before to kind of bring context of what is Calcite. Calcite does all the front parts of your query execution. So it does the parsing, so it includes the JDBC driver, it does the parsing, and then you can provide plugins to it, right? It's really an optimizer framework. You can do a lot of things with it. So that's one of the ways you can use Calcite. And so you write plugins. So one of them is going to be schema plugins. How do you provide metadata about various tables? That could be things like mutable data like Parquet. It could be mutable tables like HAs, Hadoop, Cassandra. And so you would have schema plugins, and then you have optimizer role plugins for the optimizer, and some of those rules will be specific to the storage layer. How do you push down filters, projections, aggregation, and some of the rules will be specific to the execution layer. It's like, hey, what are the characteristics of the joins this query engine knows to do? And then once you feed that and you provide costs, estimates, and the optimizer will do its magic, it's kind of dynamic programming, trying to explore the space of all of these small queries in a smart ways and spit out the best feasible plan you can think of to then execute on that layer. So you have a bunch of integration with storage layers, and you know, typically Arrow is something that lives in the execution layer. To give some context, and for either as an in-memory columnar representation to do fast vectorized execution, or serialization-free data exchange between nodes to avoid the CPU cost of serializing the serialized data. So if you want to look at, to give you where Calcite is used, so Calcite is the optimizer in Hive, in Apache Drill, in Apache Phoenix, which is SQL inside HAs to query really fast your data in HAs. It's used in Calvin, which is a cube materialization database. And it's also used in a bunch of streaming SQL use cases. So typically in streaming SQL, you don't have any blocking operators, but you cannot do in order by in streaming SQL typically, but you can do group by, you can do filters very efficiently, so a bunch of streaming SQL operation implementation that depend on Calcite. In the storage aspect, you have a bunch of immutable notions, so you can have row-oriented with Avro, you can have column-oriented with Parquet. Typically, they can live in HDFS or in S3 or other cloud storage, the GCS or something else. You have also mutable implementation with Kudu of HBase. But the key part of this is they will all share the same, from a query perspective, the same storage abstraction to the query engine. And this is the notion of push down, right? So data set as a schema. And then you want to push down to the storage layer. What are the columns you're actually querying? Because usually there are a bunch of columns, but you need only a small subset of them. What is the filter you're executing? And possibly what are your aggregation? So the goal is really to minimize the I/O to a minimum and avoid this snowplow approach of scanning all your data. So if you have columnar data, it's really easy to do projection, which is really only the columns you need. And if you have statistics, if the data is sorted, if it's partitioned, then you can evaluate the predicate on the metadata and avoid reading a lot of data, so reducing I/O a lot. And typically, you can push down aggregation. So this is kind of usually a third priority. But you can also push aggregation to the data, and that's avoid like sending a lot of data on the network. And just because typically the result of the aggregation can be implemented in a vectorized way directly while scanning and sending only the result of that. So if you think of how distributed database works, so that's kind of this diagram could represent how Apache Drill works. So you would scan, parquify, do push downs of feature, projection, materialize arrow representation in memory, and then do, like if you take this example of a SQL query where you do an aggregation and sum, you would do partial add, so you pre-materialize the output for each of the machines. Then this is really equivalent to how a shuffle works in MapReduce, where you send all the data for the same key to the same machine on the reduce side, and then you can do the final aggregation and send the data to the user. And typically, you would have Calcite on optimizing the query, generating the plan, and Arrow to send data without incurring any serialization cost, because the representation in memory is the same that on the wire. And so there's transformation-free sending of data, and then eventually it gets to the user. So now that's kind of trying to give context of what those common components are, where they fit in the ecosystem. And now we're going to take a step back and look a little bit at this ecosystem as a whole. Right, so I had this diagram you're going to see in a second, which I'm trying to make this whole approach to what the data infrastructure look like and try to make it a little less dry. So, you have your applications in the cloud, right? And you have events, so what people are doing. Maybe they're searching for something, maybe they're clicking on something. And so it sends events as little raindrops that will feed the streams of your stream processing and eventually go in your data lake. You have your batch processing going on as these water mills here. And so now that you see this other picture, this one may look a little less dry, right? So you can see like, oh, another kind of stretch analogy. And so, you collect data, you have your stream persistence. Let's say you use Kafka and you use Avro to store data in it. And you have stream processing that's going to consume that data, produce derived data sets. Eventually, it all gets archived in your at-rest storage that may be S3, that may be HDFS, could be using Avro or Parquet, or maybe it's abstracted out by Iceberg. And then similarly, you would have batch processing consuming that and producing derived data set. And one of the key things that you notice are putting also all this data API thing, one of the things you want is really generating this stable abstraction notion. So with Iceberg and metadata layer, like Marquez, actually it's Project Marquez for this. You can understand your lineage, you can abstract out the data location, because I'm sure you've all been witnessing those jobs when you read a data set, and by reading a data set, you depend on the exact file format, you depend on the exact file layout, you know, the way you predicate pushdowns, and you put the stars in the right place in the past to reading the right partitions. And the way, you know, you have to know it's Parquet, you have to know it's Avro, and like when your infrastructure team comes in and like, oh, we're going to convert everything to Parquet, and you're like, oh, what is this giant coordination project to convert everything? No, we're going to stick with CSV because it's just easier. So really, it's just about, we need this table abstraction again, like databases at a good point. And so introducing this table abstraction, and that gives you lineage, that gives you independence from formats, that gives you independence from mutability of the data, and really in a GDPR world when you expect to be able to delete some of that data, that's really important. And you know, that's kind of the core of your ecosystem in this. So that was my view on that kind of architecture. And so I'm going to take a glance at some of those things in the ecosystem we're still trying to do, when things we have started and we need to improve, or things we are just getting started at, and things that I think we may be doing in the future, but I'm not quite sure. But I think if I start talking about it, maybe people will think it's a good idea and we're all going to build it together. So we're still improving on the better data abstraction, but I hope after today you're all going to start using Iceberg. And on our end, we definitely want to use Iceberg, and on top of that, we're building this metadata repository called Marquez. It provides two things. It provides this data abstraction, but it also provides lineage, and it provides kind of the base for understanding how do we operate better, how do we understand our dependencies, how are we going to trigger the right job based on that. So it's kind of, based on that, you have better abstraction on the table. You don't need to understand the format, the layout. You can actually have snapshot isolation semantics, like in the database. You don't break every time you change something. And you can have common pushdown implementation that are actually consistent across systems. Another thing is better interoperability, and that's where Apache Arrow is really trying to help. And one of the key reasons for Arrow is a lot of those processing systems are moving to columnar and memory representation so that they can take advantage of vectorized execution. And Arrow is about pushing this across the ecosystem by standardizing this representation so that we don't spend our time converting to one representation to another. Things like, think Apache Kudu is columnar, and Apache Drill uses an in-memory columnar representation. And from the beginning, it was reading columnar data, materializing rows, sending it to the columnar engine, and converting from rows back to column in memory. So lots of inefficiency that comes from lack of standardization and trying to be compatible with the old paradigm of row-oriented execution. So Apache Arrow is still getting adopted. It's already making PySpark much faster by avoiding all the default serialization motion. It's used in Apache Drill. It powers the Parquet C++ reader to have very efficient reading of Parquet in pandas and in-memory pandas execution. The other thing is better data governance that we need to improve a lot. I think GDPR may be very obvious, but our industry is still maturing. And it's like, oh, what do you mean we need to know where our user data is and what we do with it? So I think it's just like a lot of common sense. And so as part of lineage and understanding our data and having better access control, better user consent recording, and better understanding of what we're doing and labeling jobs and data set appropriately, we can improve that a lot. So some prediction more on the technical side. I've been talking about these common properties of storage. And today we have a lot of the notion of pushdowns. on things, and really, whether you have immutable or mutable storage abstraction, you have a bunch of things that query them in the same way, expecting those common pushdowns, common schema evolution capabilities, and efficient interoperability. And that's where Arrow can really shine in providing a common data access, in presenting the data. You already have columnar data in a lot of those. So having a vectorized pushdown of features and projection, produce that as Arrow record batch and sync that to all those query engines that exist. And you could put that in a service layer. That way you avoid, like today, the implementation is all of those systems implement the pushdowns themselves directly on top of Parquet, so it's very inconsistent. Like different systems care about different optimizations, so depending on what you're doing where, it behaves differently. And I think Iceberg is the first step of it, and the next step is putting it into a service layer. So that's just my prediction, but if you think that's a good idea, come talk to me and we can maybe make it a reality. The other thing is all those notions of pushdowns we talked about, they make as much sense on the streaming than on the batch layer. So today people write to Kafka and then you archive to two different layers. But really the raw-oriented streaming aspect makes sense if you're reading the tip of your stream. Like very soon after, it's going to make sense to read, to convert it to columnar representation so you can get more throughput. If you don't care about this very low latency of getting the record as soon as possible, then you will care more about throughput. And that's where Arrow will give you more throughput by enabling vectorized execution. And then after a while, you want to move it to the tier storage on disk and move to a columnar representation like Parquet. But really from the consumer performance, we're seeing the stream and batch processing converging. Like things like Beam today, and even before Beam with Flink, you can take your streaming job and you run it on the tip of the stream. Every now and then you need to change your logic, recompute everything. And really it should not matter where your data is stored. Am I looking at the current data that's coming on my stream, or am I looking at the archive data? The logic of my job doesn't change. And a while ago we had the thing called Lambda architecture, which was really exposing all inside of this to the user. And we could really hide all of that in a service layer and take your job. And as a user, you don't need to know if you're reading the tip, you're in real time, or you're reprocessing another data, or you're catching up, and it should run your job in the most efficient environment. So it's kind of prediction of